I'm going to do a few questions out of chapter 12 and a few questions out of chapter 15. Because these two chapters kind of blend, the radical and the organometallics kind of, they're not going to be massive homework assignments. Okay? I really just want to unpack a few specific problems to give you to work out. I think we have an exam here, what, next Friday?
Yes.
Is that what it is, next Friday? Okay. So we're going to spend basically 2 lectures on this chapter, and we'll have another work day on Wednesday to solidify the 3 chapters going into the exam. Okay? I try to build this class on because there's going to be so much information at the end of the semester that's it's going to feel overwhelming. I try to build it in a way that I'm taking the important things out of the chapters, trying to teach those, and then put them into use. All right? Because trust me, once we do get into the carbonyl, it's just going to ramp up. So I'd like to try to establish some normalcy before we just start drinking too much from the fire hose. 2 reactions that we're going to see today. First one is called the Grignard. The Grignard reaction is a classic historical old school reaction. And we actually will do this in 2 weeks in lab, the Grignard. It's called Grignard. The Grignard reaction. So the Grignard reaction is a reaction that takes typically a bromide, an alkyl bromide, and reacts it with actual magnesium metal. And so when we do this in the lab, we take magnesium, and magnesium is easy to oxidize. If you remember, it loses its electrons fairly readily. So we have to strip off the magnesium oxide. So we do that with hydrochloric acid. We remove the oxide and get down to good magnesium metal. When I used to run this in the old science building, we would actually take sandpaper and actually sand off the magnesium oxide to get it to like this polished magnesium ribbon or magnesium metal. So here's what's going to happen. We've got 2 electrons between here, okay? And what happens with those electrons actually do kind of this swap, if you will. It's kind of a cool mechanism. It's a metal mechanism. And so what happens is it puts the magnesium it embeds the magnesium between the halide and the carbon. Okay? So this whole new chapter is on organometallics. Organometals or metallics. Right, that's the chapter. Organometallics. Yes?
Why do you use the proper arrow and not the half arrow for its own way?
Because it actually does both electrons go. Good clarification. Both electrons migrate. Okay, good. So, okay. Yeah, so the 0 right here, that 0 is not an electron. That's its charge. Okay, it's the metal. It's on its ground state. It's elemental magnesium. Okay. So here's why this chapter, this is a new chapter in about the last decade, maybe 15 years. We didn't have this type of a chapter in an organic textbook. It's one that's made this organic book, like I was telling you in lab, it just seems to keep getting bigger. And there's just so much, because there's so much more chemistry that we're learning. This is one area that's really, the Grignard used to be in other chapters, and it wasn't in its own standalone chapter. And here's why. When you go back and look at foundational chemistry, and you see this continuum that we spent quite a bit of time on, and that's why this is all put into this chapter. Okay, it's not very good board management, but you get the point. So, teaching this class, teaching organic chemistry through the lens of electronegativity is, again, one of those really important things. I have said several times, and I'll keep saying it, I think the 2 foundational principles, if you understand them at the core, especially chemists. Where's my other chemist? Oh, he's gone today. 2, 4, 6, 8, 10, 12, 13. Huh. wait, 2, 4, 6, 8, 10, 12, 13. We're missing 2 today. Okay, so anyway, I'm sorry, there's a little caprice there. So the 2 foundational principles, if we really want to understand chemistry, the principles of chemistry. Number 1 is electronegativity, number 2 is pKa values. All right, so that's why we're actually going to see both of those today, which is why we're going to do 2 reactions that go back in and understanding the foundations of those processes. So as a review, those that have you for GChem, the review, if not, this is new, but hopefully reviewed by some other professor. Class standard is what? 4.0. This is the highest you can get. So 4.0, we go down by increments of 0.5 across the top row. So 3.5, 3.0, 2.5, 2.0, 1.5, 1.0, right? We drop down to the B student, chlorine, 3.0. Okay, so 3.0 goes down by 0.5, 0.4, 0.3. So 3.0, 2.5, 2.5, 2.1. Now we go down by 0.3. So 1.8, 1.5, 1.2, 0.9. Okay?
Yeah.
That's review. Hydrogen's arbitrarily assigned a value of 2.1. We just memorize that. So when I look at a continuum like this, I know these are all 2.5. But this is 4.0, this is 3.5, this is 3.0, this is 2.5, this is 2.0. Watch what happens when I get to magnesium. I didn't have you memorize magnesium. Magnesium is on this table. They don't have it up here, do they? They don't have it on this one. Some good. Okay, so sodium is roughly 0.9. Magnesium is roughly 1.1. Okay, so you're really withdrawing those electrons. Remind yourself of what electronegativity is. Electronegativity is an atom's desire for electrons within the context of a chemical bond. Okay? It's the atom's desire for electrons within the context of a chemical bond. That's different than electron affinity. Remember those 2 terms we had in GChem? Electron affinity is just an atom's desire for electrons, period. So chlorine was had the highest electron affinity. It wants electrons more than anyone. It wants to really desperately fill that 3p orbital. Okay? That's why it wants it more than filling the 2p, but that's just the energetics. All right? So with that, notice what's happening here to our vectors. Because as I mentioned with these little magnets, again, this is organic chemistry. Okay, the strength of the magnet is all we're looking at. Right? We're setting up a polar covalent bond. We're moving from polar ionic, polar covalent, nonpolar, completely polar. So watch what happens here. My delta En here is 1.5, meaning this bond is really moving towards fluorine. Right? This bond is 1.0, meaning again it's moving towards oxygen. This one is 0.5. Okay? This one is 0, so it's purely covalent. So we've gone from, excuse me, we've gone from pretty polar covalent, 1.8 is considered ionic, so we're really approaching a really polar bond here. 1.0, about halfway between in our polar covalent world. 0.5, we're still polar covalent, but man, we're right on the edge. Because remember, 0.4 and below is nonpolar. Completely neutral, which is why we have no handle on the molecule, which is why alkanes are really difficult to do synthesis with, because we have no polarity. We can't react with them. Okay? Boron now, what just happened? Well, boron is an important thing. When I go from 2.0 to 1.5, boron moves the vector at 0.5, but notice what it's doing. It moves the vector the other direction. Does that make sense? By the time I get to magnesium, I am, 1.4 on magnesium? So notice on magnesium, I'm 1.4, so my vector is heading towards carbon. This is why organometallics are so important. We're going to be dealing in this chapter with organometallics. Okay, that's a metal. This is a non-metal. This is a metal. But we'll see these types of compounds. So what's happening here, and this is why this becomes so important, what happens with this is this becomes a nucleophile. Okay, that's really important. Up to this point, what's happened with our chemistry? Well, our chemistry has been carbon being attacked, something like a bromine, right? And it doesn't matter what's coming off of it. Carbon has been the electrophile, okay? So this is electrophilic. So up to this point, any kind of a nucleophile has attacked the carbon. That's what we've been doing. We've been capitalizing on the fact that this bond is being polarized in this direction in order to make carbon an electrophile. So when we get to the organometallics, we've switched. And that's why it becomes so powerful and so important. Now, it is these electrons that are going to behave these are going to behave as a nucleophile and go attack an electrophile. Okay? So this is a switch from what we've seen all the way up to this point, where carbon is being attacked. Now all of a sudden, carbon is the attacker. Okay? And that makes it very important, because here is what we want to really focus on in the year sequence of organic chemistry. The most difficult bond to make in chemistry is the carbon-carbon bond. The carbon-carbon bond is so difficult to make because, again, it's purely covalent. So the reactions that we're dealing with in organic chemistry to make a carbon-carbon bond should be flagged as special. And most of the carbon-carbon bond-making reactions have names. You know one called the Diels-Alder, right? That's a named reaction. The Grignard is another named reaction. Okay? So we'll see these special named reactions because they were hallmarks in chemistry, and the person that and the research groups that did the work oftentimes get the credit because they were special. All right? It doesn't take much to burn a hydrocarbon. It takes a lot to work with a hydrocarbon and put a handle on it that you can do further synthesis. So when I take a Grignard, depending on what the electrophile is, depends on the product that I'm going to get out. So for example, one of the electrophiles that I can work with is a hydrogen, and I'll just put, let's put, X there. Let's put, and that stands for conjugate base. Any kind of a polar protic salt, or any kind of a polar protic compound. All right, I'm going to call this a polar protic. Polar protic. Any kind of a polar protic compound. It could be methanol, ethanol, it could be an acid, it could be acetate. Is merely going to just take and remove the Grignard. It kills the Grignard. All right. So it quenches the Grignard reaction. So this is why when we do the Grignard, we have to be very careful that we don't have any moisture in the reaction. Because if you put a Grignard, a nice hot Grignard reaction, and you have water or moisture in the glassware, it quenches it and it just kills it. So next week, or 2 weeks when we do the Grignard reaction, we'll actually put our glassware in the oven the week before, crank that up to a couple hundred degrees, chase off all the water, all the moisture within. Because if you probably have done this, take like a beaker, and when you put the Bunsen burner under it, you see that all that moisture starts to come off the beaker. Because the silicon dioxide, even though in Idaho, we're pretty dry here. You know, our humidity is in the mid-20s, right? We're pretty dry. That's why our skin, you know, it starts to, it's just. But on the coast, like when I was at Berkeley, you're talking 80 to 90% humidity in the labs. So it was real. Some reactions were difficult because you had so much moisture everywhere. So you'd have to do things in dry boxes and do things on Schlink lines, which is under nitrogen. And so you had to do things just in a different way. Right, so there's the chemistry changes, the way you do chemistry, because of the moisture. Organic chemistry, a lot of reactions don't like water. All right, we use water to wash them up and quench them, or to work them up, but we don't actually use water. And there was a real push a couple decades ago for green organic chemistry. And I don't know if you noticed, if you read the lab, there's a note down below for the lab we were supposed to do this past week. It said, yeah, we tried this with bleach, but it doesn't work. We tried to go green on this one, but man, nothing compares with PVC. So, because chromium is not super conducive for the environment. So what would examples of this be? Well, again, if I took something, let me give you a specific example. So if I took something like if I took this, I took this, and acetic acid vinegar. Okay, so basically anything that has an available proton, from water to solvent to acid, it's going to take that proton. Okay. So again, it's one of the, and it's not necessarily a useful reaction, because you just killed your handle, but it is a reaction. Kind of like when we went back and we looked at AIBN, it just kind of kills the reaction, okay? But if I take the Grignard, and I react it with something like carbon dioxide, okay? Carbon dioxide is a fairly non-polar molecule, but the carbon itself is still electrophilic. So these are going to go here, and in workup, it's going to give you the carboxylic acid. Okay? So again, really nice reaction. This, by the way, if you want the full mechanism, typically it's going to be acid workup. This just grabs. That's the way. So you typically work these up in an acid wash. Okay? Nice reaction. So we just made, again, special bond. We just made a carbon-carbon bond. And that was why the Grignard back in the day was one of those, whoa, this is a great reaction. Because if I can make that carbon-carbon bond in a predictable way, I'm golden.
Where does the magnesium go?
It just goes away in the wash. It actually just washes out as magnesium halide. Magnesium, in this case over here, if you get magnesium bromide out.
Okay.
And that just goes away it just goes away in the wash.
Okay.
Yeah.
So it's just there to aid in so that way the nucleophile gets the electron.
You got it. It makes the carbon the nucleophile. Yeah, yeah. So again, kind of cool that the carbon itself is attacking.
Yeah.
Yeah. Yeah, super cool. Okay. A couple other, really there's two other main groups of reagents that we use on the Grignard. One of them is going to be aldehydes and ketones. Okay. So if I use formaldehyde, right? Formaldehyde, again under acid water wash. Okay. That is a second step because you don't want the water in that front; you'll kill the Grignard. But on the second step, on the wash, this merely puts a hydroxyl group. So we just made an alcohol. That's kind of cool. Okay. So, sorry. Has it there? No, that's good. That's good. Yeah. So it puts a carbon and an oxygen on there. If I react it with a substituted aldehyde, okay, and that dash merely just means it's a different carbon than the original carbon. Then what I get out of this with my wash is a substituted aldehyde. Oh, excuse me, alcohol. So it's a secondary alcohol. Okay? And finally, if I react it with a ketone, okay, what do you think that's going to make? See the pattern?
Oh, yeah. It's going to put 3 carbons
It's
on.
going to put 3 carbons on, good. So it's going to make a tertiary alcohol. Kind of cool, right? And then finally, and lastly, for the Grignard family, if I react it with an oxirane, which we typically in this class call epoxides, and again, you can have a substituted one as well. Okay, if I react it with that, you're going to put 2 carbons on. Isn't that kind of cool? So in this case, the electrons are drawn to the electrophile, which then protonates under wash. Does that make sense? Because the carbonyl, this is a carbonyl, I'm going to say that multiple times. Hang on, I'll let you finish writing those because I don't want to just keep talking. Otherwise it just sounds like blah, 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 blah. Like the teacher in Peanuts.
Yeah.
Right?
Yeah.
Nucleophile. That's what it starts to sound like.
You have to give the rest of the lecture to say
Yeah,
that.
boy. So I was saying, so exactly. Okay, so with that, remember going back to what we started with, we have 3.5, we have 2.5. We have a very polar bond, so that causes a delta positive and a delta. You will see this picture at least a dozen times this semester. I want that so ingrained in your thinking. I think I drew that probably 2 or 3 times in general chemistry. So it's one of those things, and we just learned recently that all of our collectively, not just you, but all of our collectively, our attention span has gone down to like 7 words or something. Now we have to say things. We're supposed to say things 15 times instead of 8 times. Isn't that crazy? Thank you, 3,000 scrolls, 3,000 thumb touches to my phone a day. Thank you very little for causing my brain now to not think. And my general chemistry students were super mad at me for not allowing laptops in there, but it's so nice. I see eyes. I see 53 sets of eyes looking at me.
Aww.
It is so neat. They're so engaged and so interactive. Okay. Okay, so here's what I was talking about. Electrons, nucleophile, and again, you can draw that either way. You can leave it as a line, or you can put the electrons in. That's all we're doing. Nucleophile, electrophile, right? No difference than base acid reactions. If you go back to even the basics of chemistry, electrons always go towards positive, okay? Electrons always go. Electrons always go towards positive, okay? This is one magnet attacking another magnet. That's all it is. It's no more complex than that. My magnets are just made because of electronegativity. Okay? That's all organic chemistry is. It really is that simple. It's one little magnetic blob reacting with another little magnetic blob. I just can predict now the blobness, right? I can predict where the blobs are going. That's all we're doing in here, okay? So this one, again, what does it do? It attacks the electrophile. This one, what does it do? It attacks the electrophile. And again, what does this do? It attacks the electrophile. Okay? Cool? All right, let's do some specific examples. Never gets old. All right. Let's see how this is going to work. Because this is, we'll add the Grignard reaction. We'll add the Grignard reaction to our toolkit, and we'll use it. Again, it's a nice reaction. It's such a nice reaction. It's a nice reaction. We'll do it in the lab. We'll get to see this reaction. Okay. Still impressed with the class, how you guys did on the deals. Oh, that was really cool. It was really impressive. Impressive lab, actually. Okay, so let's say I have a molecule that looks like this. I'm gonna build this. I'm gonna build this. Let's do this. Let's bring everything that we know so far. So I'm gonna start with an alkene. I'm gonna hit this alkene with HBr in peroxides. Actually, that's actually all done in one reaction. I'm going to hit this with because again, I want you to, again, over and over repetition, right? Repetition. So what reaction is this? Well, it's an addition reaction to an alkene, but it's a specific addition reaction. Which one is it? What is it?
Oxidative.
Oxidative. So oxidative goes Markovnikov or anti-Markovnikov? Anti-Markovnikov, okay? So that makes the terminal bromine, okay? Good? So with that, I then add it to magnesium metal, and typically this is done in ether, okay? Anhydrous ether, no water, cannot have water in there. Anhydrous means water-free. So it does it in anhydrous ether, and we buy that. Super flammable, okay? What that does is that generates my Grignard, okay? Once I have my Grignard generated, then I pick whatever I'm working with, and let's say, I pick that aldehyde, and you don't know names of aldehydes yet, but that's butanal. Let's say I pick butanal. So butanal is going to go to that carbon. Oh, can I help you out here real quickly? Hang on a second. I'm sorry. I usually, this is where I know you're going to be mad at me if you already do it. Don't. I'm going to do this. Watch, because I want you to see this. I think this case is I have colors. I think the visual on this is really important. Wait. Hold it. Make sure I get this right. 1, 2, 3, 4, 5. It's going to be 1, 2, 3, 4. So, hang on a second. Didn't give myself enough oxygen. Still, do I have enough oxygen? I don't have enough carbons, do I? 1, 2, 1, 2. Yeah, that's right. Okay, good. No, good. Because we should have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Okay? So here's the new bond that was made, right here. Okay? And then again, in the wash, you're going to get out magnesium bromide. Okay? And if I hit this with PCC, what do I get? Ketone. Boom. So check this out. I just came up with a scheme to make from an alkene to an elongated ketone. How cool is that? Isn't that pretty cool? So that's, and when we do our work day on Wednesday, we'll see this reaction. I'll say starting with propane, make these molecules. And you'll just backtrack and think, oh, those were made through the Grignard. Okay? Isn't that kind of cool? So, again, I think that's a really cool reaction. Yeah. And you know what you could do? It wouldn't be that interesting, but we'll see eventually that we can take, under hydrogenation conditions, ketones eliminate. Well, I'm not going to do that. I'll explain that one day. I'm not going to add that until we get to ketones. No, I'm not going to add ketone chemistry on top of Grignard chemistry. Okay? Good? Questions on that? Make sense?
So like,
Yeah.
you make like a polymer.
Yeah.
Okay.
It's one of the ways you can make polymers. Yeah, the Grignard. Yeah, it's pretty cool. Okay. Now, we have 20 minutes left, so we are going to be masters of pKa. Did anybody bring their textbook to class? Anybody have a digital copy of their textbook, or any hard copies in this class? No?
I have a hard copy, but I can't carry it with me.
Can't carry it with you. Didn't you used to have one with wheels?
I did,
Yeah.
but it's just books won't fit in my backpack.
No. Okay. Do you guys have the textbook?
Yeah.
You do?
Yeah.
Okay. 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 All right. So here's the thing. If you, well,
Do you want me to pull up my digital?
yeah, would you pull up your digital? Because I want you guys to see it. Pull up the front inside cover of the digital.
Yeah, exactly. And between OChem and analytical, well, that's 3 massive textbooks.
Got it? Inside glass. It has, I don't know if
That's-
digital will have it should. Very inside or the back.
Yeah, it gets unbearable on your laptop.
Okay, so part of your homework when you start to work on this chapter, reading through it, is to open up your textbook and look at the inside flap of your textbook. Does anybody remember from a GChem text the 2 most important things that we put on the inside flap of the front and the back? What are the 2 things in there?
Periodic table.
Periodic table, of course, and what's in the back? You remember what's in the back? You ever open up the back? It's really the constants. So it's your R constants, your gas law constants. It's typically things that you want to have a quick reference to. Okay, what am I, if I'm using liter atmospheres or if I'm using pascals, which R ratio? You know, it's those types of things on the other flap of a general chemistry text. Do you have it?
Yeah, the pKa value.
You got it. So on the inside flap, on the inside flap of your organic chemistry book is not the periodic table. The very first one is pKa. Okay, that's how important it is, and there's a reason why it's the number 1. On the other side of that flap are your functional groups, a list of your functional groups. Okay, so those are very important to organic chemists. Why do we put the pKa value there? Well, because in organic chemistry, if I know pKa of that proton, I know its acidity, I know how strong my nucleophile has to be to react with that. That's why it's so important. Okay? So I'll have you, and I want you to see this because I want to show you how this is going to work. We are going to deal with, I think this is in the, and I'll come back to this on Monday. I will come back, there are probably, in the pantheon of aha reactions, this is one of them. And I'll show you, and you'll see why real quickly. But if you look at the, I'm just going to do, I'm trying to think, I'm kind of rethinking how I'm going to teach this. So if you're with Dr. Nagalis, you went through alkane chemistry, you did super fun things like rotational barriers, global minima, local minima. You did these really fun things with rotating around the sp3 bond, and you would have drawn these beautiful little symmetry things, and as they rotate and things like that. Okay, you might have even talked about gauche and anti when you're doing your ring flips and fun things like that. Right? Equatorial, axial, protons on the chair and all that cool stuff. Alkanes, right? Ouch.
Did you just do an
Pop.
ACL?
I just popped my knee. That's what you get for wearing high heels. So, alkane, right? So, an alkane. So go to your pKa table and tell me the pKa of the alkane.
Here, I'll just give it to you.
God, just give it to me. That's why I wanted it. It's better if you have your textbook. I didn't bring my glasses. That's why I can't really read it. But
Zoom in.
can I zoom in?
Yep.
Okay. So if you go to the pKa table, and you're going to scroll all the way down here to the bottom, and notice the pKa of an alkane is 48. Okay? Meaning, that's not acidic at all.
No.
The higher the number, the worse the pKa. Okay? If you then go to the alkene, you'll see that the alkene is not that much better. When you go to your little trusty dusty table, you'll see that it's 44. Well, it's still really not very acidic. Meaning, it doesn't want to come off. Okay? But by the time you get to the alkyne, something changes. Notice, the alkyne is 25. Ooh. Okay? I'm just set that right there just for now. So when we get to the alkyne, we see that it's 25. Does anybody remember what water is off the top of their head? Should memorize that. I'm not big into memorizing tables. That one I would memorize. Anybody remember what it is? Anybody?
Around 15.
Yeah, good. It's 15.7, around 16. Okay, so water okay, 15.7. So watch what happens with my pKa. Because the acidity of the alkyne is 25, I'm much more acidic than the alkene and the alkane. That's why alkyne chemistry has made a massive explosion in the last several decades. Here's what happens. If I take an alkyne, I'm gonna make this a generic, I'm gonna make an R here. And I know that my pKa value of the alkyne, because I just looked it up in my table, is 25. Okay? And I try to react, or I react this with sodium hydroxide, strong base. Now go back to general chemistry. Remember I had you memorize the 8 strong bases, and in that pantheon was sodium hydroxide, right?
Mm.
Strong. And strong in general chemistry meant what?
It wants a proton.
No, I made it like strong
Oh, yeah.
is
Completely dissociates.
100% disassociated, okay? 100%, completely dissociated. That's what strong means in general chemistry. It means when I add this to water, it disassociates 100%, okay? So we know it's a strong base. But here's in organic chemistry which is really important. Is it a strong enough base to pull off that hydrogen? Okay? So is this strong base, is it strong enough to grab that hydrogen? Now here's why pKa is so important. It tells you whether or not it is. So my question is, will that go to this? And here's how we address that. Knowing the pKa of the alkyne is 25, knowing that the pKa of water is 15.7, you tell me which direction, because this is an equilibrium process, which direction does equilibrium go? Emma?
It's going to go to the left.
It's going to go to the left, big time. So this reaction goes that direction. Sodium hydroxide is not strong enough, even though it's a strong base, to pull that hydrogen off. Okay? So what do we need in order for that to happen?
A lower pK,
Lower pK or a
stronger.
stronger base. Well, it turns out, even though I had you memorize sodium hydroxide as a strong base, that's in the context of being added to water. This isn't a water reaction. We can have stronger bases. The word strong just means 100% disassociated when added to water. What happens if I were to add this proton to something like sodium amide? Well, let me ask you, which direction would this go? And here's how you're going to assess this using pKa. You know the pKa of an alkyne is 25. How do I know that? Because I went right here and I said, what is the pKa of that alkyne moving its hydrogen? It's 25. All right? So, what would my product be if I reacted this with sodium amide? And how would I assess this reaction? How am I going to assess that? What am I going to look for in my pKa table?
The sodium.
Nope, I don't, remember, I haven't looked at that one.
The pK of ammonia.
I'm going to look at the pKa of ammonia. So when I go to my table, let's see if we can find it. I don't see it. Do you see it anywhere?
They have NH3
Oh.
and NH2.
Do you see it? What is it?
38.
38.
Nice.
Holy cow. So tell me in which direction this reaction is going to go.
To the right.
Bomber to the right. Isn't that cool? What did I just do? I just made a killer nucleophile. Which is why alkyne chemistry is massively important. Watch this. Massively important. Not just little, massive. So watch. Check this out. Guess what we're going to do on Workday Wednesday? So if I take and Clayton, just for the record, I'm going to correct one thing specifically because I'm not singling you out. I don't mean this in a pejorative way. The whole class, careful not to make your alkynes like that. It's just one of those things. Remember, alkynes are linear. Okay, so I see. Again, I'm not picking on you because I see this all the time. All right, so just make your alkynes linear because that's really their geometry. Some people will shorthand them this way if you want. That's fine. I don't mind that. Just get rid of the carbons. The rule of thumb, and I don't know if the gals went over this. The rule of thumb in nomenclature is you only imply an sp3 hydrogen that is not chiral. So that's why you don't imply an aldehyde. An aldehyde is not this. And I actually do see this sometimes, and it's just, that's not an aldehyde. Okay? Technically, on alkenes as well, you don't, again, they're non-F, you don't imply, well, I get lazy and I do that, but technically, you only imply hydrogens that are sp3 carbons not, and non-chiral. So, just little, so, and I get lazy and I see alkynes like that as well. It should have the hydrogen on it, but that's just one of those little rules that rarely is it told, but it is kind of that little rule of thumb with implied hydrogens. Okay, watch what happens when I add this sodium amide, and it's done in ammonia. Okay, and I'm going to add a, let's add, hey, something I just made through my green. Isn't that kind of cool? So what happens with this is it goes to this. Okay? Because again, once I go with the sodium amide, I form this. Okay? That does a sweet SN2 displacement. And so here's the aha. I just made a new carbon-carbon bond. Right? And anytime you make a carbon-carbon bond in organic chemistry, it's a special moment. Cool? Because I can go from this now to this. Sweet. And I can even take it one step further and do what we did on Workday Wednesday, this past Wednesday. Because with this, if I would have this elongated, I know that I can hit this now with either Lindlar or sodium ammonia. Not sodium amide, sodium ammonia. Notice it's different. That's sodium amide, it only has 2 hydrogens. That's the actual base. That's going to reduce this to the alkene. And it's going to reduce this 1, 2, 3, 4, 1, 2, 3, 4 to the alkene, which again, I don't know which one, cis or trans. And then if I hit that with MCPBA, notice I go to whichever handedness I want. Isn't that cool? Yeah, that's pretty cool, because what we're going to see on Monday is if I start with acetylene, gas, acetylene being this gas here, I can functionalize it on this side, and then I can functionalize it on this side. I can make the alkyne, I can reduce the alkyne to whatever alkene I want. I still have my handle. I could even hit this with MBS, put a bromine here, and do a double elimination and make it out. I mean, it is amazing how many avenues of synthesis this one reaction opens up for us. So that's why this was a 2-reaction Friday. The Grignard and the acidity, the pKa acidity of the alkyne are 2 very monstrously important reactions for us in our organic synthesis, because once again, carbon-carbon bond formation is a special thing. Okay? Super cool.
So the carbon, this molecule on the bottom, that didn't come from the one above. It was just
No, it's just an example.
Okay.
So yeah, so if I was going to make this, my alkyne was here. So that tells, oh, yeah, sorry. That should have been, no, that's right. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, so my alkyne was there.
And then what do you would hit it with either Lindlar or?
Yeah, I don't, and again, I'd have to figure out stereochemistry, whether it was RS or RR. And that tells me whether it was cis or trans. Yeah, we'll do that on Workday Wednesday, before the exam. Yes?
So the PKAs that we used today, should we memorize those?
I would. Well, at least understand how I did that. Because there will be a question. There will be a question. Again, there's a reason why the PKAs are in a table. I'm not a fan of memorizing tables. Like I didn't memorize the periodic table. I did in high school, and that's the last time. I swore I'd never do it again. Okay? I still don't know the difference between astatine and arsenic. I think I do, but I don't use those compounds, so I have to actually look those up when I. I think, if I'm not mistaken, this one's astatine, yes, and this one's arsenic. Okay, but I don't always know that. I sometimes in GChem, I don't even know if there's 2 L's in aluminum still. Right? Anyway, that doesn't matter. There's the pKa table. If it's in table form, I typically let you use the table. Okay. The only exception to that is functional groups, because that's part of the class, but we're building on those. And by the end of the course, you're going to know an aldehyde, there's an aldehyde and an anhydride. So, okay? Yes?
I'm pretty sure you explained this before, but the hydrogen bonds with the squiggly lines.
Yes.
What does that mean?
It means, it's a good question. It means I'm not telling you the stereochemistry. Okay, it could be R or S. This tells me, in this case, it's going to be, this is S. Okay, I don't know what that is. It's chiral, but I'm not sure which one it is, and that's what that means. Good clarification. I just did some advanced organic thing on you. That's not fair. Good. Okay. All right, guys, have a great weekend. Go Rams.